Thank you.
Good afternoon. Welcome back to this afternoon session where we will have actually 4 talks. The 3 first of them will be about methods, how to invert model and look at the posterior, and then also at the model evidence or the likelihood as you have, as it was introduced. And it's my great pleasure to introduce the first speaker, which is Herman Galyulin. Herman is a PhD student at the TNU. He studied computer science and did a master in neural system for computation. And actually, his master thesis was published in Neuroimage, and you will hear about it, maybe not in his talk, but definitely in later talks throughout the week. And you might have heard of it already in class's presentation. So Herman, we're looking forward to maximum likelihood estimation.
Perfect. Thank you so much for the very nice intro, Jakob. Yeah, welcome everybody to this talk on MLE, maximum likelihood estimation, which is one of the more basic ways of fitting a model. And it's not a fully Bayesian approach, but it is something that you've heard of already from Klaus's talks and Alex's talk as well. And so many of the things that I'll talk about in this lecture, you will have heard already, which is good because you'll get used to some of the concepts in this course. So speaking of getting used to some concepts in the course, just a quick recap on the generative modeling framework that we find ourselves in. So imagine you're a researcher and you're acquiring some data from your participants. This could be, EEG, behavioral data, fMRI data. And the interesting thing about the situation is if you just look at the time series that you're acquiring, it's not something that you can immediately pass on to a medical doctor, physician, or something that you can immediately discuss in a research paper, right? So what we're really interested in is taking this data and figuring out what are the underlying biological mechanisms within our participants that gave rise to this data. So in my slides here, data, as you can see, will be denoted as Y of t. And so the entire idea is basically that we take this data and then we can build models and infer upon our parameters and hidden states where the parameters are constants in your model that dictate the evolution of the states x of t in your system, in this case biological system, that gives rise to the data that you have acquired. This is a very abstract way of looking at this diagram. So what I wanted to do is to bridge it a little bit, make it a little bit more intuitive, and specifically also connect it to some of the research that we've been working on, which is to try and use fMRI data to predict depression in simple terms. And so in our case, the data that we're acquiring are really just these time series. Again, they might look pretty, but it's not something that you can immediately interpret and understand what's going on within the brain of our participants. And then the hidden states in our system, and the reason they're hidden is because we don't actually know what's going on, what's the ground truth neural activity in our participants. But it's basically the states are the neural dynamics within these brain regions from which we have these time series. And the parameters could be, for example, the directed connection strengths between different neuronal populations. And so yeah, this is just one way of looking at this diagram. And what we're trying to do is bridge the gap between the observable and the hidden. You've already heard a lot about this from Alex's talk, which was specifically about one of the things that he mentioned, of course, is data generation. So that's where the generative comes from in generative modeling, is that you can create these models, specify a prior, and sample from that prior to synthesize data. Basically, you don't have to acquire any data. You can put these models just in a room on their own, and they will synthesize data for you, which is a really cool property. But again, doesn't get you at this idea of getting a mechanistic understanding of what's going on in your in your participants from the data that you have acquired. And to do that, we do inference. So we start with the data, and then we go back and figure out what the parameters are within our model, and then we can interpret what's going on within the biology of our participants. And so that's what this talk will focus on. I will go through arguably the simplest way of doing this, which is by maximizing the likelihood function. Another slide that I took from Alex's talk just to orient ourselves a little bit. So Alex, went through this entire adventure of creating a model, very non-trivial because you have to balance, complexity of the model with interpretability and simplicity. And so he went through, picking an initial model, prior predictive checks, et cetera, et cetera. In this talk, we will really just be focusing on fitting the model. So what is our principle? What are we trying to get at? What we're trying to do is find the parameters theta for which the acquired data y is most likely under the model M. And to put this into slightly more mathematical terms, we can look at it this way. I'll just walk you through all of these symbols here at first. So M is our model. Capital theta here is the parameter space. Small theta here are the model parameters that come from this parameter space. Theta MLE is the MLE estimate of our model parameters. So this is what we're trying to get at. Capital Y is our observed data set. Y sub t is a single observation within this data set because a lot of the time in an experimental setting, you have multiple trials. And then here, capital T is the number of trials. And so what we're trying to get at is this theta MLE, which is equal to the maximum of our likelihood function with respect to the model parameters. So basically, we're trying to maximize this term here by varying and going through the model parameter space and trying to figure out which parameters are the ones that are maximizing this function. And the likelihood here is the probability of our observed data set given our model parameters and the model. And here, this is just a little reminder that our observed data set is comprised of multiple trials. So a very mathematical, abstract way of looking at it. And so what we'll do is build some intuition by going through in detail an example, which you might already be used to because Alex talked about this. It's an example that is taken from a paper and has to do with slot machines and sort of these constant reward probabilities from these slot machines. It's from a paper by Wilson and Collins here, published in 2019. And so just to remind you a bit, what we're trying to do here in this example is understand how people learn to maximize their rewards in a case where the most rewarding choice is initially unknown. So imagine, you walk into a room, you've got two slot machines, and you basically have to figure out, do I want to play with this slot machine or do I want to play with this slot machine? And at each trial, you're choosing which one you're interacting with. And so slot machine 1 here has a constant reward probability of 0.8. So this is the probability that you will get a cash reward. So, but you don't know this, of course. And then slot machine 2, the probability of the reward, given the slot machine, is 0.2. So you'd expect that if you go in, you don't know what the rewards of these slot machines are, that over time you will basically start understanding that, okay, the slot machine 1 is giving me more cash, basically. And so you would interact with that one more. And so that's why an example data set for this experiment might look something like this. So you can see this participant here, interacting, and then over time realizes that actually slot machine 1 is pretty great. So I'm going to keep interacting with it here. And so yeah, here again, just a reminder that our capital Y, our entire data set, is the aggregate of all the trials. So now that we have an idea of the experimental setup for this example, we are going to go ahead and specify our likelihood function. And this is also something that you've already seen from Alex's talk. That's why it's called Model 1 here. Alex went through a few models. What we're going to do is revisit this example and look at it from the perspective of parameter optimization. And so this is a random choice model. It only has one parameter here, and it's really, this parameter is purely just what's the probability that you will choose slot machine 1 over slot machine 2. And so that's why you have this 1 minus b here, because it's just the converse of this. And it's a probability, so it's between 0 and 1. And so just as an example, let's say, I'm a participant in this experiment, and I interact, and then you sort of analyze my data, and then turns out that 70% of the time I'm choosing the first slot machine. And so then my B parameter would be 0.7 here. And then this here would be 0.3. And so in terms of writing this down mathematically in a single trial, or for a single trial, it'll look like this. So here's our likelihood probability of YT given our model parameters and model is equal to this this mathematical expression, which is just the Bernoulli distribution, who, by the way, is a Swiss mathematician. And so to give you some intuition about how, just plugging in some numbers here, what it would look like just to play around with this expression, I just wanted to choose a specific y and a specific theta here to show you that this Bernoulli distribution is actually very simple. So imagine your y, so the data that you've observed for a single trial is 1, aka, so it's either 0 or 1. 1 is, the black slot machine, let's say, given 0.9. So this is the parameter that we're trying to estimate, actually, but imagine that you're just playing around with this formula and you've plugged in 0.9 as your sort of model parameter. What you would get is 0.9 that comes out of this. So this is very sort of trivial, that the probability that I would choose the black slot machine if my probability is 0.9, if my model parameter is 0.9, is 0.9. Conversely, choosing the other slot machine is going to give us 0.1, which makes sense. Like if my probability is at 90%, then the probability that I would choose the second slot machine is supposed to be quite low. So that's just a couple examples to build intuition about what this likelihood function is actually doing. But of course, the 0.9 is just an example. And one thing that I want to also emphasize here is that even though this looks like a very simple model formulation, it is actually interesting to see what are the different probabilities that people end up choosing. So maybe my probability when I interact with this experiment will be different for example, your probability. And so then we can start discussing why are people choosing different probabilities when they're interacting with these slot machines. So that was for a single trial. And then if we assume that the trials are independent, what we can do is write down an expression for the entire experiment, for all the trials. And specifically, the way we can do that, because of this assumption of trial independence, is we can multiply all of the likelihoods together, all the probabilities together. And so that's why here we get this product of the Bernoulli expression here. And so again, looks pretty abstract, but really it's just a bunch of multiplications, a bunch of probabilities being multiplied together. Again, just to build some intuition. All right, so we're going to jump in to also optimizing this likelihood function. And so I wanted to do a quick reminder of what a derivative is, and also why you'll see in some slides why we're setting it to 0. So simply put, the derivative of a function is just the slope at every point. And so you can see here the tangent line in this animation is sort of illustrating what the slope is at every point in this function. And what you'll notice is right here, the tangent line becomes horizontal, meaning the slope becomes 0. And so that's why a lot of the time what we do is we try to find where the derivative is equal to 0, because that's where the, a lot of the time, the maximum of a function is. And another quick reminder is that you have, of course, functions which are not differentiable everywhere. And so here are just some examples of functions where you cannot take the derivative at every point. And this is just important to keep in mind for the next slide, where I will be discussing the two main ways in which you can maximize the likelihood function. So again, here we have our formulation. We are maximizing over the parameter space. And one way to go about it is analytically. So you can find an analytical solution. And to do this, we first ask ourselves, is the likelihood tractable? What this means is, can you actually evaluate the function at every point, or is it maybe too computationally expensive, or the function is too weird to actually evaluate it properly? And is the likelihood differentiable everywhere? And this is what I was talking about in the previous slide. Can you actually take the derivative everywhere? If you can, then you can go for this analytical solution where you take the derivative of the likelihood with respect to theta and figure out where it's equal to 0 to help you find the maximum. You can also go for a numerical solution. So this is if your function is, maybe it's a funky function, or it's not possible to do it analytically. You can go for this numerical approach where you use one of these software packages in your favorite programming language, and then implement the likelihood and then find the maximum that way numerically. And so one thing to keep in mind here is that, of course, numerically, you're always going to have an approximate error in your solution. Just going to grab some water here. Okay. So those are the two approaches. The approach that we're going to take here, because we have a relatively simple setup, is this analytical approach. And to start us off, we're going to use something that's very widely used, which is to do a log transform. And I'm going to walk you through why we do this. Specifically, when you're multiplying a bunch of probabilities together, you can imagine some of these probabilities might be pretty small. So maybe you're multiplying 0.01 with 0.0001, and then if you keep multiplying these probabilities, these numbers might become extremely small, and they might become very difficult to work with. And so the idea of a log transform is that you take these multiplications and you can do this log transform, which has this nice property that it'll take these multiplications and turn them into additions. And so that's why here, this mathematical rule, it's just showing that if you take the log of a product, it'll turn it into a sum. And so what we can do is take our original formulation here and apply the log. That's what you're seeing here, applying the log here. And then you can see the log pops inside past this product and turns it into a sum, which is sort of makes it a lot nicer to work with. And then another property of the log, which is very useful, is that it's strictly monotonic, which simply means that the maximum doesn't change if you apply the log. And so to give you an example of that, here I have plotted just a very simple function in red, and then the log transform of that function in blue. And so you can see the maximum stays at exactly the same spot. And so we're going to take advantage of this as well. Basically, we can log transform our formulation, maximize, find where the maximum is, and that'll stay the same as in the non-log transformed formulation. Great. And so if you remember, this log came in, changed the product to a sum, and then we're going to apply this log to our Bernoulli distribution that we talked about before. And some more sort of logarithmic rules is that it brings the exponents down, and when you have a multiplication inside of a log, it turns it into an addition outside of the log. And so that's why we get this formulation here at the very end. So that was the log transform. And now what we're going to dive deep into is actually maximizing the likelihood function, taking the derivative, and setting it to 0. So this part is going to be very step-by-step, might be pedantic at points, but in the age of throwing things into AI and ChatGPT and letting it do it all for you, I wanted to show you that you can actually do this all manually on paper, and you can understand how every step works. So here we go. We've got our log transform, and what we're going to do as a very first simple step is, because this is the sum of the whole thing, we're just going to split up the sum. So then we got the sum here plus the sum of this. Then we're going to, because the sum is over this t here, what we can do is bring these logs outside of the sum. So that's what we've done in this step here. We're just bringing the logs outside of the sum. And now finally, we're ready to take the derivative with respect to theta and find where it's equal to 0. And so what you'll see here is that we're taking the derivative of this entire thing that we had before. To simplify it a little bit, we're going to bring the derivative inside as well. So now we're taking the derivative of this here, this log and the sum, and then the derivative of this log and the sum. And now we're going to actually do some calculus. So we're going to take the derivative of the log, which comes out to, so log of theta is 1 over theta. And then the log of 1 minus theta is this here, negative 1 over 1 minus theta. Because, yeah, that's one of the rules, is that the log of x is the derivative of it over over x. And now we're going to do a sneaky fraction trick, which is that you can always multiply a fraction by 1 over 1. But in this case, what you can do as well is multiply it by whatever you choose over that same thing. So in this case, you can do 1 minus theta over 1 minus theta. And so that's the same as 1 over 1, and you can just multiply that fraction there. So what we're going to do with this fraction, and just the reason that we're doing this is so that we can factorize some of these symbols out and then simplify the expression. And so what we're doing here is we're multiplying this fraction by 1 minus theta over 1 minus theta. And then this fraction we're multiplying by theta over theta. And then what you'll notice is by doing this, we get a common denominator here that we can factor out, which is this theta multiplied by 1 minus theta. And so that's exactly what we do. We factor it out. And then the nice thing about having a 0 on one part of the equation is that you can divide that 0 and it'll stay 0. So what we're going to do is divide both sides by this 1 over theta 1 minus theta, get rid of it. That's great. And so we have this much simpler formulation now, where we have 1 minus theta times the sum minus theta times the sum. And of course, what we can do is multiply, sort of get rid of these parentheses and multiply the sum. So that's why we have here just the sum itself. That's the 1 here, minus theta of the sum. So that's multiplying the sum by this minus theta here. And then same thing here. We're splitting up this 1 minus yt. And so we get this formulation. So that's that same formulation. What you'll notice here, and this is always nice, is when you see two terms, a negative term and a positive term that are exactly the same, that means you can cancel them out. So that's awesome. Let's get rid of those. And so now we're getting quite close to our solution. We've got this thing here. You can think about what is, if you just have a sum of 1, what does that equal to? Well, that's just the same as t, right? And so now we have this sum minus theta t, bring over the theta t onto the other side. And then finally, we have our MLE estimate, which is, going from here to here, we're just dividing both sides by t. And so that's why we get this final MLE estimate, which is, if you look at it, it's just the arithmetic mean of your data. And so intuitively, what this means is that the MLE estimate is the same as the percentage of times that you choose the first slot machine. So for example, if like I said before, if I'm choosing the first slot machine 70% of the time, our MLE estimate is going to come out at 0.7. And that's how we're going to sort of set that model parameter that we were going for. Great. So just to zoom out a bit, what are some of the advantages of MLE? And then we'll go through some limitations as well. So the first one is that it's easy to compute. There were a lot of steps if you do it manually, but from a computational perspective, it is easy to compute. It's a simple optimization problem. It's interpretable. As you saw, the MLE in our simple example was just the arithmetic mean of the data. So we understand sort of intuitively what that means with respect to the model parameters. And it has some nice mathematical properties. So Asymptotic here means what happens in a situation where you have infinite data. And so mathematically, what you can say is that the MLE comes out as consistent. So you recover the true parameter value, which is very nice, and it's efficient. So you have the lowest possible parameter variance out of all estimators. And it's invariant to reparameterization, which means that if you transform your model parameter space, then the transformed MLE for that space will stay valid. So those are just some nice mathematical properties. One thing just to sort of do some foreshadowing here is that, of course, in real life, you don't always have infinite data. And so in reality, these mathematical properties don't always come about as something that you can use in practice. So some limitations of MLE is that it is a point estimate, meaning that you don't have a representation of uncertainty. And this is, again, some foreshadowing as to why taking a fully Bayesian approach might actually be quite useful. The MLE might not be unique, or it might not even exist, depending on properties of your likelihood function and parameter space. So definitely something to keep in mind there. And then a very important one is overfitting. And so that is, as I said in the previous slide, you don't always have, well, you never have infinite data. You have a finite set of observed data points. And so if you have a small amount of data, then chances are MLE is going to overfit to that data, meaning it will fit it, but it'll overdo it to a point where it will not be able to generalize to a novel situation or to new data. And so what I want to do as the last part of this talk is walk you through and demonstrate this overfitting situation with maximum likelihood estimation. So again, overfitting, it's limited to finite observed data points, unlike in the asymptotic property. We don't always have infinite data. And to demonstrate this, we will use a polynomial model. So you'll see in the next slide, it's actually quite simple. This is just a mathematical abstract way of looking at it. So we'll take a look at a polynomial model of order P. So your order is just the highest exponent in your polynomial. And also, just to make this formulation seem a little bit more intuitive, you can think of it in terms of the first slide that I showed you. So the y is your observed data, the thetas are your parameters, of course, and then x are your hidden states. And so this is how a polynomial would look like in that situation. Plus, we'll add some normally distributed noise. And then this here is just a more compact way of looking at this polynomial model using some vector multiplication. And so the important thing to keep in mind with this model is that as you get a higher order of the polynomial, you start getting more degrees of freedom. So your model has more degrees of freedom, meaning that it can express itself in a lot more ways. And we'll see a very concrete example of that coming up. So this is going to illustrate one specific polynomial here. So you see this line here on the x-axis, we've got our hidden states, y-axis, we have our observed data. And on the bottom right here, you'll always see the specific polynomial that we're talking about. So in this case, we have this polynomial 0.3 minus 0.1x plus 0.5x squared. This is what it looks like. And on the right, these bars are the thetas here. So that's why you see 0.3, 0.3, negative 0.1, negative 0.1 here, and 0.5 here. And so the idea here, again, is I'm going to demonstrate to you how overfitting happens in an MLE context. So imagine we have this polynomial, and we sample some data from it. Here we have some data points along that line. This is not with noise yet, so let's add some noise. There we go. We've added some normally distributed noise. And so now let's get rid of that polynomial that we started with. So in this situation, you can imagine you've just gathered some data from a participant. You have these data points. You have no idea what the underlying process was that generated these data points. So you can think of it sort of that way. And now what we're going to try to do is look at different orders of polynomials and how well they fit the data. So if we start with a p equals 1 polynomial, so you can see here, very simple, right? obviously doesn't do a great job, but it's very simple. It doesn't have many degrees of freedom. And so this is sort of the line you get in a very simple case. Let's go up to p equals 2. So that's what this polynomial looks like. And you can see with p equals 2, it's actually sort of recovering. So again, what you see here is the MLE estimate of the parameters, and you can see it's recovering them pretty well. So here, the black bar is what we started with, what was our ground truth model. And then in orange, we see what the estimates are. And so here on the bottom right, you also see what the estimates are, quite close to what we originally had. But it is also true that this line isn't actually going through each data point perfectly. And so you might think, well, my model's not doing that great. It's actually not hitting every single data point. And so maybe what I should do is increase the expressivity of my model even more. And this is what happens when you do that. So now we have a very large polynomial here of order 7, which is also the same order as the number of data points, which is a recipe for overfitting. But what you can see here is that with this, this large sort of amount of expressivity in this model, what happens is the model parameters also start getting really large. So they sort of start exploding in a way. You see the 700 here. And this is also a clue that there's something going on. There's some overfitting going on. And so, but at the same time, it is hitting every single data point exactly. And so what happens if you sample some new data? You'll see that, of course, it has the yellow line has overfit and doesn't properly generalize to new data. And so the question is, in general, how do we avoid this situation? One of the ways we can do this is by constraining our model parameters and the expressivity of our model, or in other words, constraining the degrees of freedom in our model and not allowing our model parameters to explode in this way. And that's where some of the Bayesian approaches will be quite useful. So yeah, that was just demonstrating some overfitting where it doesn't generalize to new data if your degrees of freedom are too large. And so to link this back to our favorite Bayesian formula here, what we've just done is only maximized the likelihood. And so the question is, can we constrain our model parameters using other parts of the Bayesian approach? And just a side note, the idea of constraining your model parameters within the setting is also called regularization. So that's a term that you might come across. And so the question is, can we use the full Bayesian approach to regularize our estimates? And so, of course, the answer is yes. There are ways to do that. One approach is called this maximum a posteriori estimation, MAP for short, where you get a point estimate of the posterior. So instead of maximizing this likelihood here, you take the joint, so you include the prior in your estimation as well, and then that gives you a point estimate of the posterior, which one of the limitations of that is that you still don't get an idea of the uncertainty. And so because you're estimating the joint here, the likelihood and the prior, under a flat prior, the map is actually equal to what we just did in the entire talk, which is MLE. And so what we can do is go a step further and also include this term in the denominator here, which is the model evidence, with approaches like variational Bayes and sampling Bayes techniques, which gives you the full posterior density, so you also get an idea of the uncertainty in your estimate. And so I will stop here because Lionel will dive deep into some of these approaches, and I will definitely let him do that. So thank you, everybody, for listening to this talk on MLE. I'd like to acknowledge my TNU colleagues, of course, specifically Florian, who gave this talk last year, and Stefan and Katarina, who gave it before, and of course, everybody at the TNU who gave me feedback on this presentation as I was preparing it. And just a reminder that after the last lecture tomorrow, we will be going bouldering. So if you would like to join for that social event, please feel free to, after the last lecture tomorrow, I'll be outside and we'll sort of get a group together and go together. Great. Thank you so much.
Thanks a lot, Herman. I didn't want to make Herman nervous up front, so I didn't tell you in the beginning that this was his very first CPC talk. So you did very well. Congratulations on that, Herman.